Every single day, modern global enterprises generate an overwhelming high-velocity stream of digital financial transactions across systems. But this information is stored across completely distinct software environments, specifically built for payroll, tax, and procurement systems. Despite having access to more raw data than ever before, compliance teams struggle to detect hidden regulatory risks and increasingly sophisticated fraud. This raises an immediate question. Why do sophisticated natural language processing algorithms fail to catch these enterprise-level fraud patterns? Accumulating massive amounts of data yields no analytical advantage if the systems evaluating that data cannot communicate with each other. Look at this split-screen comparison of current compliance systems. On the left, a traditional workflow evaluates payroll, an invoice, and a tax filing independently against static rules. A payroll record might perfectly match all internal regulations and receive a green checkmark, appearing compliant in isolation. However, modern enterprise fraud rarely manifests as an obvious error within a single file. Fraud typically takes the form of a structural contradiction, exploiting blind spots between systems. Mapping relational lines between identical documents reveals a hidden pattern. Evaluated together, previously compliant records reveal glaring inconsistencies, intersecting and contradicting each other. Because the fraud exists strictly between the documents, any system focused on isolated document parsing is mathematically guaranteed to miss these relationships. To solve this structural blind spot, we require a 3-layer AI framework designed specifically for cross-document intelligence, beginning at the very base data layer. The first component is the graph-based entity correlation engine. Flat document tables break apart, reforming into a complex graph structure. Nodes represent entities connected by relational edges. This connects related entities, like employees, vendors, and accounts, across distinct ERP systems into one unified network. The primary function of this layer is to answer a single foundational query: what is connected? Mapping this relational topology exposes structural anomalies and patterns that flat file analysis cannot see. The next analytical hurdle involves geographic scale. Global enterprises operate across vastly different geographic and regulatory frameworks. Identical transaction patterns will generate entirely different risk signatures if they are evaluated in different currencies or under different regional tax codes. This requires the second architectural layer, Cross-Jurisdictional Normalization. This layer translates conflicting schemas into a single standard. It standardizes currencies, harmonizes reporting periods, and aligns classification schemes into a universal vector representation, turning mismatched labels into a clean visual language. Without this universal translation, an AI would generate false positives based on formatting differences rather than actual fraudulent activity. Once the enterprise data is connected and globally standardized, the system must evaluate the actual risk without relying on brittle binary rules. This is achieved by the final architectural layer, the adaptive probabilistic risk model. The standardized graph network begins to pulse as connective edges glow red based on historical data overlays. The model calculates risk by evaluating multiple simultaneous signals, prioritizing metrics like anomaly strength and historical source reliability. Instead of a simple pass-fail alert, the system generates a prioritized, confidence-based numeric risk score. Probabilistic scoring ensures investigators focus strictly on mathematically significant compliance threats, effectively silencing the noise of minor irregularities. This architecture evolves based on its own operational outcomes. Human auditor decisions, both confirming fraud and flagging false positives, are actively routed back into the core system, feeding directly into the probabilistic risk model. When auditors confirm a case of fraud, the relational pattern is strengthened for the future. When a human marks a false positive, the model automatically recalibrates its weights, mathematically reducing similar future alerts. This feedback loop creates a continuous learning cycle, allowing the enterprise compliance system to become structurally more accurate with every audit completed. To test this architecture under real-world conditions, researchers evaluated approximately 3 million financial records spanning 5 years across 4 different regulatory jurisdictions. The framework achieved a 91% precision rate alongside an 87% recall rate during the evaluation. These results produce an F1 score of 0.89, proving the capability to identify true fraud while minimizing misdetections at an enterprise scale. The system delivered a 76% reduction in false positives compared to traditional rule-based approaches, alongside a 40% drop in manual audit efforts. This architecture rescues compliance teams from thousands of wasted investigative hours by automating the detection of multi-system contradictions. Implementing cross-document graph correlation and probabilistic modeling provides the architecture required for predictive governance. Traditionally, compliance identified issues after audits or regulatory reviews had already concluded. Mapping inter-document relationships allows organizations to quantify what is statistically likely to fail before a breach occurs. By quantifying this relational risk in real time, the system anticipates structural vulnerabilities right before they can trigger a regulatory breach. Enterprise compliance now operates as a continuous intelligence function, moving at the same speed as the transactions it monitors.